Today we're going to talk about another type of test known as the integral test. We already know about three different major ideas for series. The first is the test for divergence, which tells us that if we have a limit as n approaches infinity of a sub n, and this limit does not equal 0, then we know that the series diverges. However, if that limit equals 0, that tells us nothing. Of use, anyway. And so what you have to do is resort to another test. We also know things about the geometric series. The geometric series is of the form a times r to the n minus 1 power. And if that r value is between -1 and 1, or if its absolute value is less than 1, then we know that the series converges. If it doesn't meet that requirement, it diverges. Now, the harmonic series, which is of the form 1 over n, we know this one's special because it always diverges. So that's just a quick review of the three main ideas we've talked about already, and today we're going to add in the integral test. Let's think back to improper integrals, specifically the integral from 1 to infinity of 1 over x to the p. Now p is the exponent, and it can be any sort of value, but we're going to kind of divide it into two ideas. The first is if p is greater than 1, and the second is if p is less than or equal to 1. If p is greater than 1, we found that the area under the curve, or the integral, converged, meaning it had a finite area. We found that if p was less than or equal to 1, for example 1 over x in this image here, we see that it has an infinite area, or that it diverges. So we're going to use this idea to help us with series. We begin by investigating the series whose terms are the reciprocals of the squares of positive integers. For example, 1 over n squared. You can see that this is the reciprocal of the square of our positive integers, 1, 2, 3, 4, and so forth. And each of those is being squared in the denominator. Now, there's no simple formula for the sum of these first n terms, but the computer-generated table to the right suggests that the partial sums are approaching a number near 1.64. And you can see that as our n values approach infinity, our sum seems to be approaching 1.64, approximately. Now, this means that it looks as if the series is going to be convergent. We can confirm this impression with a geometric argument. If I were to say that there was some function that followed the path of our series, so here are some points for our series. Each of these points represents a part of this particular series. This point would be at the n value 2. This second point would be at the n value 3, and so forth. So what's happening here is we're creating a geometric representation by, in a way, relating this to area under the curve. And we're doing so by creating these rectangles again. Each of these rectangles has a width of 1, which is right here. So each of these 1s represent the width of the rectangles. And each of the larger portions, the fraction pieces, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, etc., that's showing the height of each of our rectangles. And we know that in order to get the area for each of our rectangles, we can take the width times the height, and that would give us the area of our first rectangle. The width times the height would give us the area of our second rectangle, and so forth. And as we add them up, we would get an approximation for the area underneath this curve, or an approximation for our series. Now, this calculation would need to go on until infinity because that's what's happening with our series. Now, we do see that these rectangles are an underestimate for the curve, and so this approximation is going to be an underestimate of the actual area. And although this estimation is not quite the series we're working with, we can kind of finagle it so that it matches it a little better. The area estimation that we have up above, if you notice, is starting with rectangles beginning at end value 2. So really it's only taking into account this portion of the series. So we need to try to add in the first end value, which would just be a value of 1. So we need to add in a value of 1 to our area under the curve as well. And when we do that, we see that 1 plus the area under the curve. Now let's recall, we did calculate this idea here in a prior section. So we would have to change that into a limit statement. Take the antiderivative evaluated at t and at 1, and we would get the area as 1. So we do know that this particular antiderivative's area is 1, and by adding that first rectangle that we really didn't include because of our right-handed rectangles, that area that was missing, that first part of the series, that first part of the sequence, I guess, if we add those together, 1 plus 1, we get that the sum of the series should be less than 2. And that's what we're seeing here in this table of values as well. So you can kind of tie in the idea of area under the curve to these series, and you're really going to do so by doing these improper integrals. So now let's take a look at the series 1 over the root of n. The table of values of this series suggests that the partial sums are not approaching a finite number, so we suspect that the given series may be divergent. So as you see here over here in the table, as our n values are approaching larger and larger numbers, or as they approach infinity, it doesn't look like our partial sums are really converging to any particular number. They don't seem to be converging. And so to tie this into the area, again, this time doing left-handed and overestimate idea to see if we do have a divergent series. If we do an overestimate areas, we are going to start at the value 1. So we're actually starting with the exact 1 for our n, and we're still going to have a width of 1 for each of our rectangles, and the height of each of our rectangles is going to be the value as given. So it's going to be 1, and the height of our rectangle is going to be a sub 1. And the width of our rectangle for each of these is going to be 1. So our next rectangle will have a height of the a sub 2. So 2, a sub 2, and so forth. So here's our first rectangle and our second rectangle and our third rectangle, and you can see that the addition of all of these really is just our series written from 1 to infinity of 1 over the root of n. And so because this is an overestimate, we can relate this to the improper integral. And if I were to go through and actually do the improper integral like I did above here, we would find that the improper integral is actually divergent. And because the area approximation is greater than the improper integral calculation, and we know the improper integral is divergent, then that would force the area approximation, which is greater, to be divergent as well. And let's recall that this area approximation is really just the series. So this is really telling us that the series is divergent. And that's with p-values less than or equal to 1. So these two examples kind of tie right back into what we saw before with improper integrals. Now this brings us to the integral test. The integral test states, suppose that f is a continuous, positive, decreasing function from 1 to infinity, and we're going to let a sub n equal our function evaluated at n. Then the series from 1 to infinity of a sub n is convergent if and only if the improper integral is convergent. So in other words, if the improper integral of the function that would essentially match our sequence or series is convergent, then our sum or our series is also going to be convergent. And if it is divergent, then the series would be divergent. Now, when we use the integral test, it is not necessary to start the series or the integral at the n value 1. It is also not necessary that f always be decreasing, but what is more important is that f will ultimately be decreasing. That is, decreasing for x values that are larger and larger than some number n. And then finally, we should not infer from the integral test that the sum of the series is equal to the value of the actual integral. All the integral test is telling us is whether it's convergent or divergent. It doesn't tell us what the sum of the series is actually equal to. And here's an example of that. Here we have a series from 1 to infinity of 1 over n squared, and we're being told that that's equal to pi squared over 2. But if we take the integral of the function for the same series from 1 to infinity, that actually equals 1. These two values are not equal. Pi over 2 divided by 6 is not equal, or pi to the second divided by 6 is not equal to 1. So there's just one example that disproves the idea that the integral would give you the sum of the series. That is not what we should think. We should only think that this is telling us whether it's convergent or divergent. So let's see an example. Now, as we do examples for this, I'm going to try to go through each of the tests to give it some sort of procedure for you to follow should you not really know how to attack a problem to begin with. However, if you see something that you think is immediately going to work, this isn't a necessary thing to go through every single one of these ideas prior to getting to the idea that you want to use. So all I'm doing is going through these to kind of help if you're not exactly sure where to start. So the first thing I'm going to do is talk about the idea from a prior section, which was the test for divergence. We'll be able to use the test for divergence, and if it works, then I will answer this question right away, which is telling whether this series converges or diverges. So let's recall that the test for divergence has us take the limit as n approaches infinity of our series, of our sequence, 1 over n squared plus 1. And we need to see what this would equal. Well, I know that my numerator would stay constant, my denominator would get awfully large, so this would approach 0. Now, remembering back to the test for divergence, if it equals 0, this tells us nothing. And so that means we need to go to another test. So the test for divergence wasn't exactly fruitful. Another idea that I talked about at the beginning that we mentioned in prior lessons is determining whether we have a geometric series, which in this case, this does not look geometric. It doesn't have that a times r to the n minus 1 idea going on there, so it's not geometric. And we need to think, is it harmonic? And the answer is no, it doesn't seem to have that 1 over n form to it. So the only other test that we know and what we can try now is the integral test. So we're going to try to employ that. Now the integral test, remember, is to take this 1 over n squared plus 1 and put it into an improper integral from 1 to infinity and just replace those n values with x's, making it into a function. Now we know from our prior lessons that you can't just evaluate this with an infinity as a part of the integral. We have to change this into the limit as t approaches infinity and change our bounds from 1 to t. Now we can take the antiderivative of this. The antiderivative of 1 over x squared plus 1 is arctan. Oops, I forgot to write my limit statement. So now we can take a moment and evaluate this at t and 1. So we'll get, keep forgetting to write my limit statement, don't want to forget that. So arctan evaluated at t minus arctan evaluated at 1. Now we can kind of use the idea of the limit to say, okay, well, we're really looking for when arctan is equal to infinity. Okay, so at what angle does the tangent equal infinity or have some sort of asymptote? So we need to think back to the graph of arctan here for a minute. And remember, arctan kind of has this shape to it with asymptotes kind of happening at those values. And these values are pi over 2 and negative pi over 2. Now, because we're working in the positive idea, we need to stick to the pi over 2. So arctan at infinity would really give us the value of pi over 2. And arctan evaluated at 1 is saying at what angle does the tangent equal 1? And that is at pi over 4. So our answer here is going to be pi over 4. Now, this isn't telling us this is the sum of the series. This is saying that it's converging because pi over 4 is a nice simple number, right? And so because we're getting pi over 4, we can then state, so therefore, since the integral test, or excuse me, since the integral converges, not the integral test, since the integral converges, let me write this properly. And the fact that it's converging to pi over 4 is really no matter. It's all we needed to know is that it's converging. Since the integral is converging, we can say the series will also converge. And then you need to state what test it is that told you that information. So we would say the integral test. Okay, so that is our answer. Pi over 4 is not our answer. That's just telling us that it's converging as an integral form. So we know that the series is now converging because the integral converged through the integral test. Now let's look at example 2. For what values of p is the series 1 over n to the p convergent? So we need to look when p is less than 0. So let's start with the test for convergence. So if we were to take the limit as n approaches infinity of 1 over n to the p, now let's remember that our p-values are less than 0, so that would mean they are negative. Negative p-values would push this piece in the denominator up to the numerator, right? So that would mean that that is just growing and growing and growing as n is approaching infinity. So this would mean that we are divergent because it's approaching infinity. And this is by the test for divergence. Remember, the test for divergence states that if it's not equal to 0, it is divergent, but also, of course, if it does not exist, it's divergent as well. Now, let's try the limit at if p is equal to 0. So this will be the limit, again, using our test for divergence to see what's happening here, of 1 over n to the 0 power. Now we know that 1 over n to the 0th power is really just 1. And so therefore we would have a limit of 1. And because 1 is not equal to 0, we can say that this is divergent, again, by the test for divergence. Now, that was when p is equal to 0. Now let's look to see when p is greater than 1. So here we have the limit as n approaches infinity of 1 over n to the p form. And again, p is greater than 1. And so if you recall back from, I believe it's lesson 7.8, if we were to try to take the derivative of this, or excuse me, the limit of this, we would see that the denominator is growing really large, and so it would approach 0. So the test for divergence is telling us nothing here. So it tells us nothing, the test for divergence. So we're going to have to use something from lesson 7.8. We're going to have to try the integral test now and force this into an integral. And I keep saying lesson 7.8 because we did this integral in lesson 7.8, 1 over x to the p form. And in lesson 7.8, if you were to look at that, looking back to what we did before, for example, this one, 1 over x to the p, where p is greater than 1, for example, 2, we saw that it converged, right? This one converged to 1, for example. And you would see that this was an idea from lesson 7.8. So we know that this is going to converge if p is greater than 1. And again, you might want to mark that if you want to look up where that came from, that is from section 7.8, actually doing the math behind that. But the idea here is that we employed the integral test, took this series here, put it into an improper integral, 1 to infinity of x over p, and we have this idea, this improper integral, converging if p is greater than 1 from section 7.8. So you can kind of see some interesting ideas happening. And what this does is it relates to our next test. So note, in order to use the integral test, we need to be able to evaluate the improper integral from 1 to infinity of f of x dx, and therefore we have to be able to find an antiderivative of f. Frequently this is difficult or impossible, so we need other tests for convergence too. And one of these important tests for series is called the p-series. and it is of the form, the sum from 1 to infinity of 1 over n to the p power. Now the p series tells us that it is convergent if p is greater than 1, which is kind of what we just saw here, right? And it is divergent if it is less than or equal to 1, which is pretty much what we saw in some of these examples. Not all of them, but some, the less than or equal to idea. So this p series will help us with many different types of series. So let's see an example in example 3. Example 3 is a p series because it does have the form 1 over n to the p. We can see that it is a p series, so I'm going to make note of that. I can see that the p-value is the exponent, which is 3, and I know that 3 is greater than 1. And because 3 is greater than 1, we can tell that it is going to converge according to the rules above. So we can finally state that it converges because p series, with p greater than 1. So let's look at B. This is another p series. It again has the form that we're looking for of 1 over n to the p power. Our p value is the exponent, which is going to be 1/3, which in this case is less than or equal to 1. And so therefore, because it's less than or equal to 1, according to our rule, we know that it's going to be divergent. Again, you always want to write your reasoning because it's p series. Keep leaving off my S. P series with p less than or equal to 1. Okay, so now let's do a couple of example 4. Some of these we'll do in class, some of them we'll do as groups in class, and some of them we'll do on the video. So now let's do another example to determine whether these converge or diverge. We're going to do example 4A. So example 4A, we're going to start with the test for divergence. So like I said, I'm often going to start with the test for divergence, and that will hopefully help us kind of come up with a more prescribed way to run through these. But again, if you can jump straight to one because you think it's just going to work that way, that's fine too. So we're going to start with the test for divergence, which is when n is approaching infinity of the limit, in this case, of the ln of n over n. And this, of course, would be infinity over infinity if I were to try to evaluate this. So I'm going to need to enact L'Hopital's rule. And I'll take the derivative of the numerator and denominator. So that'd be 1 over n over 1. And so that, of course, would simplify to 1 over n, which would give me 1 over infinity, or 0. And again, we know that the test for divergence, if it's 0, tells us nothing. So we need to try something else. The next ideas that we have are some of the different types of series. So we need to ask ourselves, do we have a geometric series? And the answer is no. This is not of the form for geometric. Do we have a harmonic series that 1 over n? 1 over n? And the answer again is definitely not. Do we have a p series where it's 1 over n to the p power? And the idea is no, we don't have that either. So sadly, none of our specific types of series will work, so we're going to have to attempt this using the integral test. So we're going to change this into an improper integral from 1 to infinity of the ln of n over n. Whoops, sorry, the ln of x over x We're doing this in terms of x, which means we're going to have to make it into the limit as t is approaching infinity from 1 to t, because you have to change your bounds when dealing with your improper integral. Now this is going to be a little bit of a u substitution question, believe it or not. So for our u substitution here, my u is going to be the ln of x. My du is going to be 1 over x dx, which I actually have both of these. So this is a very nice u substitution. I can kind of just do this off to the side, actually. It'd be the integral of u du, which would end up being u squared over 2. And then if I, of course, put back in my ln, this would give me the limit as n approaches infinity of the ln, or excuse me, 1/2, I need that 1/2 from the division by 2 there, ln of x squared, and we're going to need to evaluate that at both t and 1. So that is what we'll do. So now we have the limit as t approaches infinity of 1/2 times the ln of t to the second power there, minus 1/2 times the ln of 1 to the second power. Now, the ln of 1, of course, is 0, right? So this would all go to 0. And the ln of infinity would be infinity, and then infinity squared would be infinity, and infinity divided by 2, or times 1/2, would still be infinity. So really, it's just infinity minus 0, which would just be infinity. So this is actually telling us that we diverge. Okay, so now we need to state our statement here. So since the integral converges, the series will also, or excuse me, diverges. I said converges and I mean diverges. So since the integral diverges, the series diverges by the integral test. And that's all there is to it. Now let's look at 4b. So 4b is the series for 9 times n plus 8 over 9 times n plus 1. And we're going from 1 to infinity. So once again, I'm going to start with my test for divergence to see if this will lead us to the other side and get us to the end. And if not, then we'll have to work our way down. So the test for divergence here is putting this as a limit. And we'll do 9n plus 8 over 9n plus 1. Now, if I were to plug that in, I see that I get infinity over infinity. So once again, L'Hopital's rule is going to come into play. Now again, if you see this using those pre-calc ideas, because of our n is approaching infinity and you have the equal degree of your numerator and your denominator, you could use that idea to take the ratio of the coefficients, but in my opinion, it's in this case just as easy to do L'Hopital because the derivative really is just, in this case, 9 over 9, which would give us a limit of 1. Now, because the limit is 1, we know that that is not equal to 0. And because we're using the test for divergence, and the test for divergence says if the limit is not equal to 0, then we know it diverges. So we have actually answered this question super quickly. So therefore, the series diverges by the test for divergence. And that is just about as simple as it's going to get. Okay, let's do 4C. So 4C is the series from 1 to infinity of 6 over n to the 0.78 power. Now, if I were to try this using the test for divergence, and hopefully you're seeing that this is actually going to be something special, right? And not necessarily a test for divergence. But if I were to do the test for divergence, you know, as I said, kind of doing that prescribed pattern here, and it's fine to do that. I would see that my numerator stays the same, denominator is going to infinity, so I would be equal to 0, which this would tell us that I would need to do another test, right? It tells us nothing. So I'm going to go to the next one on my list. My next one on the list is to say, hey, is this geometric? And the answer is no, this is not of the geometric form. A times r to the n minus 1 power. Is this harmonic? And the answer is no, this is not 1 over n. So then we have to ask ourselves, is this a p-series? And exciting for us, we can say, yes, it is. Okay, it is of the form 1 over n to the p power. We have a coefficient, yes, of a 6, but our p is going to be 0.78. So let me try to rewrite this. So here we have the sum of 6 over n to the 0.78. And if I just take that 6 and pull it to the side, we are now perfectly in that p-series format. And so this is telling me that my p is equal to 0.78. So let's kind of run through the idea of the p-series. Do we have a p-series? We sure do. What is our p-value? Our p-value is 0.78. 0.78 is less than or equal to 1. And so because 0.78 is less than or equal to 1, we know that this is going to diverge. So we write, therefore, the series diverges because it's p-series with p less than or equal to 1. And there you have it. So that is what we had to talk about for the integral test. So hopefully you can remember the test for divergence, geometric, harmonic, now the p-series as well, and of course the integral test.